Welcome to the Deep Dive. We're the show that takes a whole mountain of information, sifts through it, and boils it down to the core insights, just for you. Today, we're diving into a really epic story of engineering. Just picture this. It's the early 2000s, Google's growing like crazy, and they're facing this data challenge. Well, like nothing anyone had ever seen before. We're talking billions of web pages, petabytes of data scattered across literally hundreds of thousands of, regular inexpensive computers. This wasn't just a big data problem, it was the big data problem. Existing file systems, they just couldn't cope. Tweaking wasn't enough, they had to invent.
Exactly. And that invention, the thing that really underpinned everything, was the Google file system, or GFS. It's kind of the hidden engine that let Google make that huge leap to what we now call web scale. And they did it using, like you said, readily available, off-the-shelf hardware. Pretty amazing stuff.
So, our mission today is to unpack how GFS was designed really from the ground up to tackle Google's specific, massive data needs. We'll look at the assumptions they challenged, some quite radical, and the, well, frankly, brilliant design choices they made. Let's dig in. Okay, so to really get GFS, we first have to understand the why, right? What was so different about Google's situation that made them just ditch conventional wisdom?
Yeah, that's the core of it. GFS wasn't just an evolution. It was driven by seeing things completely differently from traditional file systems. Maybe the biggest insight was this. At Google's scale, component failure isn't an if, it's a when. Actually, it's a constant.
That's fascinating. Because normally you kind of assume the hardware is basically reliable, but Google was like, nope, with thousands of cheap machines, stuff will break all the time. So what did that mean for the design? What core principle came out of that?
It meant that things like constant monitoring, error detection, fault tolerance, automatic recovery, they couldn't be add-ons. They had to be integral to the system, right from the start. They were dealing with everything: app bugs, OS bugs, human error, disks failing, memory glitches, network issues, power supplies, you name it. Failure was just the normal operating environment.
Wow. That's a huge philosophical shift. What else was unique about their data?
Another really key thing was file size. GFS wasn't dealing with lots of little KB files. It was routinely handling multi-gigabyte files, trying to manage, billions of tiny files across terabytes or petabytes. That would have been totally unwieldy.
So files were just huge, which forces you to rethink really fundamental things like I/O operations, block sizes, the basics. But it wasn't just size, right? It was also how the files were used that was different.
Precisely. Most of the time when files were changed, it was by appending new data to the end, not overwriting existing stuff. Random writes. Pretty much non-existent in their main workloads. And once data was written, it was usually read sequentially, start to finish.
Huh. That's a very specific pattern. So the implication there is you can focus your optimization efforts laser sharp on making appends fast and atomic, right? Like ensuring they fully complete or not at all. And maybe traditional caching on the client side wasn't as big a win for them.
Exactly. And this leads to something really interesting. Like, Google had this unique advantage because they controlled the whole stack. They could co-design their applications and the file system together. This let them do things like relax the consistency model for GFS in certain ways and introduce totally new operations like an atomic append feature because they knew how the apps would use it.
That flexibility sounds incredible. Must have simplified GFS in some ways and enabled really powerful things for their distributed apps. And one last point, you mentioned Google's apps cared more about throughput.
Yeah, absolutely. For the kind of batch processing Google was doing, high sustained bandwidth, moving lots of data over time, was way more important than super low latency for every single little operation. And you see that priority reflected throughout the whole GFS design.
Okay, so that sets the stage, the why. Now let's get into the what, the actual architecture. You said the core components are pretty simple.
Deceptively simple, yeah. You've got a single master. Think of it as the brain. Then lots of chunk servers, they're the muscles, doing the storage work. And then numerous clients, the applications using the file system. And the really cool part is these are all just standard commodity Linux machines, often running GFS as user-level processes. No special expensive hardware.
Amazing. Just off-the-shelf boxes. So how do they break up and store the files on these machines?
Okay, so files get divided into these fixed size pieces called chunks. And the size they picked was 64 megabytes.
64 megs. Wow, that's way bigger than typical file system blocks.
Oh, yeah. Much, much larger. The master gives each chunk this immutable, globally unique 64-bit ID, the chunk handle. And the chunk servers, they just store these chunks as regular Linux files on their local disks. Nothing too fancy there.
And for reliability, which we know was key, they replicate these chunks, right?
Absolutely. Every chunk is copied onto multiple chunk servers. The default is 3 replicas for fault tolerance, but you can configure that, make it higher if needed.
Now that single master, it sounds like a potential bottleneck. How did they stop it from becoming the weak link in such a huge system?
That's one of the most clever parts of the design. The master does manage all the metadata. We're talking the file namespace, access controls, the mapping of files to their chunks, and critically, where those chunks are currently located. It also runs the whole show managing chunk leases, which control write access, doing garbage collection, migrating chunks around for balance.
Okay, but how does it avoid getting swamped with read-write requests?
The key decision was minimize the master's involvement in the actual data flow. Clients only talk to the master for metadata, like where are the chunks for this file. All the heavy lifting, the actual data transfer, happens directly between the client and the chunk servers.
Got it. So for a read, the client asks the master, hey, where's chunk X? Gets back a list of chunk servers, caches that info, and then it talks straight to the nearest or best chunk server to get the data.
Exactly. This cuts down the load on the master dramatically. For a huge file read, you might only hit the master once at the beginning.
Okay, let's go back to that 64 millibit chunk size. Why so big? What are the wins? And were there any downsides?
The advantages are pretty significant. First, like we just said, it drastically reduces how often clients need to talk to the master. One metadata lookup can cover a huge chunk of data for sequential reads. Second, it means clients can often keep a persistent TCP connection open to a chunk server for longer, which is more efficient network-wise. And maybe most importantly, it reduces the amount of metadata the master needs to track. Fewer chunks per file means less mapping info, which helps allow all the metadata to fit in the master's RAM.
All metadata and RAM. That must make lookups super fast.
Lightning fast, yeah. But you asked about downsides.
Yeah, what's the catch with huge chunks? Small files, maybe?
You got it. Even with lazy space allocation, where space isn't actually used until written, a large chunk can be problematic for small files if they're accessed by many clients at once. Think of like an executable file used by hundreds of batch jobs starting simultaneously. If that executable fits in one 64 megabit chunk, the few chunk servers holding that chunk can get hammered. We saw that happen.
The hotspot problem. So how did you deal with that in practice?
Couple ways. For files like that, we just replicate them more heavily, store them on more chunk servers to spread the load. We also tweaked the batch system to stagger the job start times a bit, so they weren't all hitting the file at the exact same microsecond. Long term, there was even thought about allowing clients to pull data directly from other clients in those cases, kind of peer-to-peer.
Makes sense. Practical solutions for a practical problem. Okay, so GFS is built on these cool ideas, but how does it work? Especially around managing that metadata and ensuring consistency.
Right, this is where the master's design is really key. Keeping all metadata, namespace, mappings, everything in memory is central. It's not just for speed on lookups, it makes background tasks way more efficient too, scanning for garbage collection, checking replication levels, rebalancing chunks across the cluster.
But RAM is volatile. How do you make sure that critical metadata isn't lost if the master crashes?
Persistence is crucial, yeah. So the namespace and the file-to-chunk mappings are made durable by logging every single change to an operational log. This log isn't just stored locally, it's replicated to several other machines before the operation is confirmed back to the client, so it's safe.
Okay, operation log for persistence. But you mentioned something really counterintuitive earlier. The masters doesn't persistently store chunk locations. How does that even work? How does it know where anything is?
It sounds weird, right? But it's actually a brilliant simplification. Instead of trying to maintain a perfect persistent map of which chunk server has which chunk knock, which is hard when machines are constantly joining, leaving, failing, restarting, the master just asks. When it starts up, it polls every chunk server. Hey, what chunks do you have?
Yeah.
And then it relies on periodic heartbeat messages from each live chunk server to keep its in-memory map up to date.
So it rebuilds that location map dynamically.
Pretty much. It simplifies things immensely because the chunk server is always the definitive source of truth for what's actually on its disks. If the master and a chunk server disagree, the chunk server wins. It avoids complex synchronization problems during failures.
So that operation log really is the single source of truth for the metadata structure.
Absolutely. It's the only persistent record of the metadata changes, and it defines the global total order of concurrent operations, replicated, flushed to disk. It's the bedrock.
Let's talk consistency. GFS is often called relaxed. What guarantees do you get?
It provides specific, well-defined guarantees, even if they're different from traditional POCX systems. File namespace changes, creating files, renaming those are atomic. They fully succeed or fail. Successful data mutations are guaranteed to be defined, meaning the write completes, the data is consistent, and all clients will see that same written data. The nuance comes with concurrent successful mutations to the same region. Those are undefined but consistent.
Okay, undefined but consistent. What does that mean in practice? Like, what would an application actually see?
Think of it like this. If two clients write to the same chunk at the same time, without proper coordination, all the data from both writes will end up in the chunk, and all replicas will look identical. But the data might be interleaved in some unpredictable way. It's consistent in that everyone sees the same final result, but the exact content might be a mix of fragments from the concurrent writes, not necessarily one write followed cleanly by the other. And of course, if a mutation fails on some replicas, the region becomes inconsistent.
Okay, that makes sense. And that record append operation sounds really unique.
It's a game changer for certain apps. It guarantees an atomic append at least once. The key is, GFS picks the offset where the data gets appended. This totally eliminates the need for complex locking or coordination between multiple clients, all trying to append to the same file, like in producer-consumer queues or log merging. GFS handles making sure each record lands atomically.
So how do applications cope with this slightly looser data consistency?
They're built for it. Apps tend to rely heavily on appends rather than overwrites. They use checkpointing to know which parts of a file are definitely consistent. And, critically, they often write records that are self-validating, containing checksums and self-identifying maybe with unique IDs. This lets the application reading the data detect and handle any potential issues, like duplicated records from retries or padding inserted by GFS around appends. The apps make themselves robust.
And when a write or an append actually happens, how does GFS coordinate that across the replicas to keep them in sync?
That's managed using leases. The master grants a time-limited lease, say 60 seconds, but extendable to one of the replicas for a given chunk. This replica becomes the primary. The primary is then responsible for deciding the serial order for all mutations, writes or appends, to that chunk. All other replicas, the secondaries, just follow the order dictated by the primary.
Right. And you mentioned earlier the data flow is decoupled from the control flow for writes. Can you walk through that again?
Sure. It's pretty clever for network efficiency. Step 1. The client asks the master for the primary and secondary replicas for the chunk. Step 2. The client pushes the actual data to all replicas primary and secondaries. They just store it in an internal buffer for now. This uses the network bandwidth efficiently, potentially in parallel. Step 3. Once all replicas acknowledge receiving the data, then the client sends the actual write request just to the primary.
So data first, then the instruction.
Exactly. Step 4. The primary picks a serial number for this write, ensuring sequential ordering for concurrent requests. Step 5. The primary applies the write locally, in that order. Step 6. The primary forwards the write request and the assigned serial number to all the secondary replicas. Step 7. The secondaries apply the write in the same serial number order. They report success back to the primary. Finally, the primary reports success or failure back to the client. It's this separation that allows high throughput.
That's a really elegant flow. Okay, beyond the core mechanics, GFS has some powerful extra features for robustness, right? Like snapshotting.
Yeah, snapshotting is super useful. It uses the standard copy-on-write technique. So creating a snapshot of a huge file or even a whole directory tree is almost instantaneous and uses very little initial space. People use it all the time quickly, creating copies of massive data sets for experiments or checkpointing application state before trying something risky.
And what about placing those replicas? You mentioned trying to survive rack failures.
Right. Replica placement isn't random. GFS tries hard to maximize reliability and availability. The main goal is to spread replicas across different physical racks in the data center. That way, if a whole rack loses power or its network switch fails, which definitely happens, you're unlikely to lose all copies of a chunk. The master considers rack diversity, but also things like disk space usage on the chunk servers, how recently chunks were created. It's constantly trying to keep the system balanced and resilient.
And the garbage collection is lazy. Why not just delete things immediately?
Well, when you delete a file in GFS, it doesn't immediately reclaim the space. It first just renames the file to a hidden name, adding a timestamp. Then, after a configurable delay, usually something like 3 days, the master really deletes it from the namespace metadata. Only after that are the underlying chunks considered orphaned, and the master tells the chunk servers they can actually delete the chunk data during their regular scans.
So what's the benefit of that delay?
Several things. 1, it's simpler and more reliable in a distributed system where things can fail during complex operations.
Yeah.
Deleting immediately is harder to make robust. 2, It spreads the cost of dilution over time. It becomes a background activity. And 3, it's a safety net. If you accidentally delete a huge important file, you typically have that grace period to undelete it. Saved people many times, I bet.
Definitely sounds useful. And how do you handle replicas that might be out of date, maybe because a chunk server was down for a while? Stale replicas.
GFS uses chunk version numbers for that. Every time the master grants a new lease to a primary for a chunk, it increments the chunk's version number and tells the replicas. If a chunk server comes back online after being down, its replicas might have older version numbers.
Yeah.
The master knows this because the chunk server reports the versions it has. The master simply won't use those stale replicas for reads, and it won't send write requests to them via the primary. Eventually, they'll get identified as bad and garbage collected, replaced by up-to-date clones.
The fault tolerance seems really layered. Beyond replication and fast recovery, what else? You mentioned shadow masters.
Yeah, fast recovery is key masters and chunk servers are designed to restart in seconds. But for the master, the operation log and checkpoints is also replicated. And yes, there are typically shadow master processes running. They replicate the same log, apply the same changes slightly behind the primary master. They don't accept writes, but they can serve read requests for metadata if the primary master is temporarily down. It improves availability for reads.
Okay, but here's a really critical point with commodity hardware. How do you trust the data on the disks? How do you prevent silent corruption?
Ah, yes. This is super important. Checksums. Each chunk server independently verifies the data it stores using checksums. Each 64 millibyte chunk is broken down into smaller 64 kB blocks, and each of those blocks has its own checksum stored alongside it. When a client reads data, the chunk server retrieves the data and its checksum. It verifies the checksum before sending the data back. If the checksum fails, the big red flag. The chunk server tells the client and the master there's an error. The client then just asks for the data from a different replica, and the master will then arrange for the corrupted replica to be replaced by cloning from a good one.
So checksumming catches errors on reads. What about writes and appends?
It's optimized for appends. When appending, you only need to compute checksums for the newly added blocks incrementally. Overwrites are rarer, but would require recomputing checksums for affected blocks. And there's one more really cool thing, idle scanning. Chunk servers periodically, in the background, read and verify the checksums of chunks they store, even if nobody's actively reading them. This allows them to detect corruption in infrequently accessed data proactively before a client actually needs it. It really helps maintain long-term data integrity.
That proactive scanning is clever. And finally, the tools to figure out what's going wrong.
Diagnostics. Absolutely essential in a system this complex. GFS logs a lot of information, RPC requests and replies, significant events like servers going up or down. It's done efficiently, sequentially, asynchronously, so the performance impact is minimal. But having those detailed logs is invaluable for debugging, isolating problems, understanding performance. You can reconstruct exactly what happened.
Okay, so we've got the why, the what, the how. How did this all perform in the real world? Did the benchmarks back up the design?
Yeah, the micro benchmarks were pretty solid.
Yeah.
On their test cluster, reads could hit an aggregate rate of about 94 millibases across 16 clients reading from one GFS instance that's like 75% of the theoretical gigabit Ethernet limit between the switches involved. Impressive saturation. Writes were around 35 millibases aggregate for 16 clients. A bit lower, maybe half the theoretical limit, partly due to some inefficiencies in the Linux network stack at the time when pipelining writes across the network to multiple replicas. Record appends performed well, often limited by the network bandwidth available to the specific chunk servers holding the last chunk of the files being appended to. But apps usually worked around this by appending to multiple files concurrently.
Yeah, those production clusters you mentioned, A and B, the scale was just immense.
Oh yeah, hundreds of chunk servers in each. Cluster A had about 18 terabytes of actual file data stored. Remember, that's replicated, so raw disk usage was higher. Cluster B had around 52 terabytes, huge amounts for the time. And remember the metadata discussion. On these massive clusters, the master's metadata was still only tens of megabytes in memory, roughly 100 bytes per file on average. It really proved the master wasn't a memory or CPU bottleneck.
And recovery. If a chunk server died in one of those huge clusters.
The recovery times are critical for keeping things running smoothly. In one test, they killed a chunk server holding about 15,000 chunks, 600 gigabytes of data. The system restored all the lost replicas onto other servers in just 23.2 minutes. Even more impressively, they simulated losing 2 chunk servers holding some chunks that were then down to only 1 replica, the most dangerous state. GFS restored those critical chunks back to 2x replication in just 2 minutes. That speed is vital for high availability.
Wow. And did the actual workloads match the design assumptions? Lots of reads and appends.
Exactly as expected. The analysis of real workloads showed the vast majority of operations were large streaming reads and large sequential appends. Overwrites were really rare, mostly just clients retrying writes after a transient error,
Yeah.
not applications intentionally overwriting data.
Yeah.
It really validated the focus on append performance.
And you mentioned war stories, challenges with the commodity hardware and Linux itself.
Oh, absolutely. Dealing with commodity stuff wasn't always easy. There were subtle bugs, like certain combinations of IDE disk drives and Linux kernel versions had protocol issues that could cause silent data corruption.
Silent corruption, that's terrifying.
It really is. Data gets written, no error reported, but when you read it back, it's wrong. That experience was a huge motivator for building in those robust checksums at the GFS layer. They couldn't trust the hardware or OS perfectly. There were also Linux kernel issues they bumped into, like the sync system call, which forces data to disk, becoming surprisingly expensive for very large files. And a single reader-writer locked deep in the kernel could sometimes cause timeouts across the distributed system, which they eventually traced and fixed using Pred.
So even though they hit these snags with the commodity parts, having the Linux source code available was a massive advantage.
Absolutely invaluable. It let Google engineers dig deep, understand the root causes, work around them, and even develop patches and improvements that were often shared back with the open source community, a real benefit of building on open source.
So pulling it all together, what's the big picture takeaway from this deep dive into GFS for someone listening?
Well, GFS wasn't just a file system. It was really this foundational layer that enabled Google to handle data and innovate at a scale nobody had reached before. And crucially, it did it using cheap, standard hardware.
And the core philosophy seems to be embrace failure, don't fight it, optimize ruthlessly for your actual workload patterns in their case, huge files, lots of appends, and leverage the ability to co-design the system with the applications that use it.
Exactly. Those are the key lessons.
GFS really shows us that sometimes the biggest breakthroughs don't come from polishing existing ideas, but from fundamentally questioning the basic assumptions when faced with a radically new challenge. Which leaves us with a provocative thought. What other assumptions are we making in technology today, things we take for granted that might be holding us back? What rules could you break in the problems you're facing to maybe unlock a completely new kind of solution?